Welcome to The Explainer. Have you ever actually stopped to wonder how the digital world manages to process literally billions of actions, messages, and transactions in the blink of an eye? The secret isn't just raw processor power. The reality is, our digital world runs on these hidden blueprints, invisible architectures that dictate exactly how information is stored and retrieved. Today, we're jumping right into the fascinating world of data structures, and we'll see exactly how computers manage massive amounts of data without just completely crashing under the weight of it all.
Here's the roadmap for today's explainer. We're going to kick things off with the million-item problem, define what data structures actually are, take a look at the array, pit lists against dictionaries, and wrap up with the ultimate speed and memory trade-off. All right, let's get into it.
So, I want you to picture an inventory database for a store, and it's got exactly 1 million items in it. If an application needs to find just one specific item, and it's forced to search through all of them one by one, it's going to hit a wall. When your data grows to this kind of scale, 1 million or more records, relying on a sequential, one-by-one search just becomes a massive bottleneck. Which brings us right to part one, the million-item problem. Because at the end of the day, scale changes absolutely everything in computing. It's the fundamental crisis of scale, right? As data grows, search naturally becomes slower. Now, sure, modern processor speeds are ridiculously fast, but they still fall short if you're dealing with data in the billions. Imagine a web server where thousands of users are all simultaneously trying to search a massive database. Without a specialized system, the application has to search sequentially. It's kind of like looking for one specific book in a completely unorganized library of 1 million books. Even the fastest librarian on Earth is going to fail at that. We clearly need a better system. And that system is exactly what we're covering next in part two, what are data structures? At its core, a data structure is just a systematic way of organizing and storing data so it can be accessed and used efficiently. By giving your data a specific, logical layout, you're massively reducing the time it takes to do things like search, sort, insert, or delete information. You're not just throwing data into a pile, you're actually structuring it with an interface and an implementation that dictates exactly how it behaves.
When you look at the whole landscape of data structures, it really divides into two broad categories. First, you've got primitive structures. These are your basic building blocks built right into programming languages, things like integers and floating point numbers. Then, on the other side, you have non-primitive structures. These are the more complex architectures built out of those basics, and they branch down into linear lists and non-linear trees. This whole taxonomy basically represents the toolkit we have to solve that million-item problem.
Let's zoom in on one of the most foundational non-primitive structures we have. Part 3, the array memory's workhorse. Think of a computer's memory kind of like real estate. An array packs data tightly together in contiguous, side-by-side memory locations. It's exactly like a street lined with identical row houses. Because every single element in the array is the exact same size and type, the computer's processor doesn't actually need a search at all. It just uses a simple mathematical formula, taking the base address of the first house, adding the size of the data multiplied by the index, and boom, it instantly calculates the exact address of any element. What's super fascinating to me here is the sheer history behind this concept. Arrays are fundamental to the history of computing itself. Back in 1945, when they were building the very first stored program computer, computing pioneer John von Neumann actually wrote the first array sorting program. Arrays effectively exploit the raw addressing logic of computers, which is why they are the absolute bedrock of modern programming. But of course, there's a catch. Arrays provide what we call constant time, or big O of 1, access, provided you know the index. It's instant. But what if you don't know the index? What if you're searching by the actual value? Well, that brings us right back to linear time, or big O of n. So the crucial takeaway here is this. If you know the house number, getting there is instant. But if you only know the resident's name, you still have to walk down the street knocking on every single door until you find them. So how do we get around this problem of knocking on every single door? Let's move to part 4, lists versus dictionaries. If you've ever coded in a language like Python, you've probably asked yourself this exact question at some point. Why does a dictionary feel so much faster than a list? Seriously, when you're checking if a specific value exists, asking a dictionary feels light years faster. But why is that? To understand why, we have to look under the hood. A list is essentially a dynamic array. It stores items in a strict sequential order. So to find something by its value, it has to perform a linear scan, big O of n. It starts at the beginning and checks every single item.
A dictionary, on the other hand, is built on a hash table. When you look up a key, the dictionary runs a mathematical hash function on it to compute a direct jump point to the correct storage slot. It doesn't scan through earlier elements at all. It literally teleports directly to the answer. That gives us roughly constant time, or big O of 1, average case lookup.
But hold on, we definitely shouldn't just throw lists in the trash here. Lists aren't inferior, they're just optimized for different things. If you tried to replace every list with a dictionary, you'd be making a massive mistake. Lists are absolutely essential when you need ordered iteration, when you want compact storage with very little overhead, or when you specifically need fast, random access by a numeric position. Choosing your data structure is really all about matching the tool to the specific operation you're trying to perform.
And that brings us to our final section, Part 5, the speed and memory trade-off. Because the ultimate unavoidable truth of computer science is that speed is never free.
This is the ultimate trade-off in programming. Arrays and lists, they give you slower, linear search times, but their space complexity is super low. They're compact, they don't waste memory. Dictionaries and hash tables, they give you that incredible constant time speed, but their space complexity is high. Dictionaries literally buy their speed by spending extra memory to maintain that complex hash table structure underneath. That right there is the golden rule. You can have more memory overhead in exchange for lightning-fast access, or you can have less structure for cheaper, more compact sequential storage. There's honestly no such thing as a universally perfect data structure. There are only deliberate trade-offs designed to solve specific problems efficiently. So we've seen how arrays use math to jump straight to memory, how linear searches totally fail at scale, and how dictionaries spend extra memory to buy those blazing fast hash lookups. The hidden blueprints of the digital world are all about making the right trade-off at the right time. Knowing this, the next time you write a script or build an app, ask yourself, what operation matters most here, and how are you going to organize your data to make it happen? Thanks so much for joining me on this explainer, and I'll catch you next time.